name's Harini and I will be your lecturer for 1-2 Methods in this video. And just letting you know, this lecture is brought to you by ATAR Notes. If you don't know what ATAR Notes is, this is just a little bit of a summary of what we do. So we basically have a lot of free resources for students to access to sort of help with their studies. And we've also been running these lectures for quite a bit of time. So you might have already attended this lecture. So if you have attended before, welcome back. And if this is your first lecture, then welcome to ATAR Notes. So we've been running these lectures for, I think, since 2015, and a lot of students have found this useful, and we've tried to really adapt them to help as many students as possible. So yeah, we really do hope that you find this lecture really useful. A bit more about ATAR Notes. So it's not just these lectures that we have. We also have a bunch of free resources that you can access by heading to the website. So there's study notes, so just hundreds of study notes that you can download and review and use for yourself. Lectures, so like this one. Discussions, so there's like online Q&A where you can discuss with other students, and sometimes tutors come on and sort of guide those discussions. We have videos, so videos about maybe even course selection and different subjects. We have newsletters, so updates about what's happening with the curriculum, what's happening with exams. We have an ATAR calculator for those of you who might be interested in predicting your ATAR. And articles, so just articles about study tips, study strategies, how to stay motivated, and all of those really important things. And a lot more, so you can just head to the website to discover more stuff, and they're all completely free. There's also some paid resources if you want to sort of take that extra step in your learning. So there's ShootSmart, which is just online classes. They're weekly, they're recorded, and you'll be taught by someone who did really, really well in the subject. There'll be study guides as well, so printed, you can buy them online, and you can have notes or you can have topic tests to revise. And Ed Unlimited, so that's a resource that I used, and it's basically sort of an online library of all those study guides, sort of all in one place. So you can check them out if they're useful. If you think they're useful, definitely worth having a look. And just wanted to say a special thanks to La Trobe Uni, RMIT, Deakin, UTS, and Macquarie. So without them, these lectures would have been quite hard to run. And the Aspire program is being run by La Trobe, so make sure that you check that out. If there's any courses in La Trobe that interest you, definitely worth applying for the Aspire program. Okay, so now let's actually get to the bulk of the lecture. So again, this is methods 1 and 2. We're going to be doing some revision of what you might have learned in term 1 and some head start for term 2. Before we get started, a little bit about me. So I'm a 2020 graduate. So I did year 12 in 2020, which means that I did most of my year 12 during lockdown, most of it online. So that was a unique experience. So currently I'm studying med in Adelaide. So I'm actually doing Bachelor of Clinical Science, Doctor of Medicine. And my subjects were physics and methods, so 3-4 physics and 3-4 methods in year 11. And then in year 12, I did 4 subjects. So I did Eco, Spec, Eng-Lang, and Chemistry. So actually, before I even get to the lecture content, just want to say that the lectures are being run a bit differently this year. So this time it's just a lecture recording, which means that, you can run it at your own pace. You can pause it when you need to. You can run it at 2 times speed or even half speed if you need to do that. So it's a lot more flexible this time. So we won't have a break today. You can pause the lecture whenever you need to. A little bit about methods. It can be a really tricky subject. I think over the years it's only gotten harder. The content hasn't really changed, but the way that VCOM wants you to apply this content, I think the expectations have gotten a bit higher. But we can work on it. It's definitely not impossible to do well in methods. It can be overwhelming, whether it's because of the sheer amount of new content that you have, or whether it's because of applying that content, knowing how to apply it and when to apply specific content. So that could make it quite tricky. It can be quite hard to manage time during exams or SACs. So that's why we want to run these lectures. That's why we want to give you tips and strategies to help you out so that we can actually make methods fun, so that you understand it and you actually enjoy applying those concepts and you know when to apply specific concepts. There's a huge overlap between 1, 2, and 3, 4 methods, meaning that a lot of the content that you learn in 1, 2 methods, so such as quadratics, polynomials, transformations, and even calculus, all of that comes again in 3, 4 methods, just a little bit of extension. So that's why I think it's a really, really important thing to solidify your understanding of 1, 2 methods. And be really confident in 1, 2 methods, or at least reasonably confident, so you feel more confident in 3, 4 methods, so you actually know what's going on. And last thing, so calculator in methods, I think is really, really important. Being able to use your CAS or Casio or Mathematica or whatever software that you use, being able to use that confidently is super important. And I'm not too sure about the Casio calculators or Mathematica, but I have used the CAS. So if you want to ask questions about the CAS, you're welcome to, and I'll be able to answer them. But yeah, so that's our goal for today. We want to try to make you more confident, even make methods fun, make it easier to apply that understanding. So we'll have practice questions, we'll have content, and maybe some calculator tips as well. So a bit of an overview for today. So we'll have 2 separate sort of blocks of content. Remember, there's no break in between. So we're just going to do one after the other. So I'm going to be talking at you a lot. So if you find it a bit, annoying to listen to or a bit exhausting, just pause, take a break, and then come back to it. So first content block, we're going to talk about sort of linear, function notation, sets, functions, quadratics, and inequalities. So I think most of it would probably be a revision from year 10. And in our second content block, we'll be talking about sort of a few new graphs. So graphs that might look a bit unfamiliar to you now. So stuff like hyperbola, truncus, square root, circles. And we'll talk about domain and range. Those are really, really important. And we'll also talk about inverse functions. Okay, so let's get started. Let's start with linear relations. So linear relation is just a polynomial of degree 1. So if you remember what a degree is, it's just the highest power of that polynomial. So let me just get the annotation up. Okay, so polynomial of degree 1, so anything with a power of 1. So this y equals mx plus c, that's basically y equals m times x to the power 1 plus c. So that's what's happening here. And here C is your y-intercept. Or actually, I should have circled the plus C. So plus C is your y-intercept. So you can have a negative y-intercept, positive y-intercept. Doesn't matter. And remember, y-intercept occurs when x equals 0. So let's say we substitute x equals 0, m times 0 plus c, y equals plus c. And m is the gradient. So if you don't remember what gradient is the slope of the graph. So it's basically how steep is it, or how sort of flat is it. Let's do this one. So solve the following for x. Let's see what's been done here. So you've got 2x plus 3 equals 2. Subtract 3 from both sides, so 2x minus 3. So 2x plus 3 minus 3 is just 2x. 2 minus 3 is negative 1. And then x equals negative a half because you're dividing both sides by 2. So being able to solve linear equations is a really important skill. Hopefully you've been working on it. I think you would have started working on solving linear equations since maybe even year 8. So it's something that you should be confident by now. An exam tip, it's a good idea to sort of highlight your answers. So either underline them or put a box around them, just so the examiner can know straight away what your answer is. Okay, so following on, you need to know how to calculate the distance between 2 points. And you just use this formula, and you don't have to memorize it. You can sort of figure it out. So let's say you have 2 points. So you've got x1, y1 here, and you've got x2, y2 here. So those are the 2 points. And here is the distance that you're trying to calculate. Okay, you've got A, B, and D. And keep in mind, this is a right angle triangle. So hopefully it's looking familiar now. AB, right angle triangle, you want to find the hypotenuse. So hopefully Pythagoras is coming to your mind. So A is the horizontal distance. So x2, so that's from here to here. x2 minus x1, that's a horizontal distance. And B is a vertical distance. So y2 minus y1. So that will give us our vertical distance in this scenario. Remember Pythagoras, a squared plus b squared equals c squared. Here, your c is basically d here in this instance because it's just a distance. So remember a squared is x2 minus x1 squared, b squared is y2 minus y1 squared, and that's equal to d squared. And then to get d, you have plus or minus square root of x2 minus x1 squared plus y2 minus y1 squared. But you can't have a distance that's negative. So a distance is always a positive value because it's sort of a measurement from one point to another. So you can't go negatively from one point to another and find that distance. So distance is greater than 0. So that's why distance is only the positive value of that square root. So distance is plus square root of x2 minus x1 squared plus y2 minus y1 squared. So here, if you ever forget how to calculate the distance between 2 points, that's okay. If you forget the formula, no big deal, because you always have Pythagoras. You can always use your logic to figure it out. So it's not on the formula sheet, so it's really important that you memorize it or you can figure out how to calculate the distance. I think it's a good idea to memorize it because it would save you time. It would save you from having to apply that logic, and you won't even get extra marks for, drawing this diagram unless you're actually asked to. So an example, so find the distance between 0.01 and 24. So first, this is the first thing, so recall that the distance formula is square root of x2 minus x1 squared plus y2 minus y1 squared. So that's the first thing to recall. Second thing, substitute your points. So your first point is 0 and 1, so that's this and this. And your second point is 2 and 4. So you don't have to actually have this step. I'd say all of this is step 2. You don't really need to show which you're substituting first and which you're substituting second. So you can just go straight from here to here and skip that step in the middle. Okay, now simplify it. Distance is negative 2 squared plus negative 3 squared, 4 plus 9. So distance is square root of 13. And remember, distance is positive, so obviously it's going to be a positive square root. Okay, so that's it for distance. Really important concept. Something that's related to distance is midpoint. So if you have a line segment, so line segment is basically you have 2 points and a line joining them. The midpoint is your middle point of that line segment. And to find that middle point, we basically average the 2 coordinates. So midpoint is x1 plus x2 divided by 2. So you have 2 coordinates divided by 2. That's the average of those 2 coordinates. And then here, y1 plus y2 divided by 2, that's the midpoint of the y coordinates. So for example, if we were to try to find the midpoint between 1 and 2 and 3, 4, so if you want, you can pause the video here and work it out yourself. So now's a good time to pause if you want to. Okay, so to work this out, substitute into the formula. Again, you don't really need this first step. You don't need to show what you're substituting first and what you're substituting second. You can just go straight and do this as your step. So midpoint is 1 plus 3. So 1 and 3. And then 2 plus 4 divided by 2. And that's 4, 2, 6, 2. And remember, midpoint is a coordinate. So make sure that you give your answer as a coordinate. Don't be like x equals 2 and y equals 3, because you're not giving the midpoint coordinate now and you're not answering the question. So it's really important that you read the question and you give that answer as a coordinate for the midpoint. Okay, next we're going to be talking about gradients. So this is a concept that's probably been introduced to you a few years ago, but gradient is your rise over run. So essentially, how much does the y increase for the every time? So let me rephrase that actually. So for every 1x, how much y is there? So every time the x increases, how much does the y increase by? So that's your gradient. It's basically the change in y over the change in x. The change in y per the change in x. So based on the change in x, how much does y change? So it's basically the slope. So for now, all you need to know is the gradient is the slope of a line. And you can calculate it as rise over run, or you can basically do y2 minus y1 divided by x2 minus x1. Both will give you the gradient. This equation here is just a way of rewriting that first one. For example, find the gradient of the line that passes between the points 1, 2, and 3, 4. So you can use the gradient between any 2 points on the graph. So it helps you find the equation. So let's actually figure out the gradient. So remember, gradient is y2 minus y1 divided by x2 minus x1. So they've decided that this is x1 and y1. And this is x2, y2. It doesn't matter which you pick first and which you do second, as long as they're corresponding. So as long as you don't do y2 minus 2 and x2 minus 3. So as long as you don't mix up those coordinates, you're fine. Okay, gradient is 4 minus 2, 3 minus 1. Again, you don't need to include this line of working out. You can just go straight to here. It might be a good idea to do m equals y2 minus y1 on x2 minus x1, depending on how many points there are. So if there are 2 marks for this question, it might be a good idea to add this as well. So show the formula that you're getting the gradient for. And then gradient is 2 on 2, or gradient is 1. So here your gradient is 1. So what that means is that every time x increases by 1, y is also going to increase by 1. If your gradient was 2, it's going to tell you every time x increases by 1, y increases by 2, and so on. So just emphasizing that, to find the gradient, you can have any 2 points on the line, and it will help you find the equation of the line as well. Okay. So gradient can also be represented using angles. So let's say you have a graph that's like this. So you've got y, you've got x, and let's say it's going like that. This is an angle. And if the angle is bigger, it's telling me that the graph is more steep. If the angle is smaller, it's telling me the graph is more flat. So you can use this angle to figure out the gradient. So you can say tan theta is rise over run. And then that theta is tan inverse of rise over run. So now we're going to talk about how we actually get that. So let's say we have a graph here. So that blue line is our the equation of our line. And that red theta, that's our angle. So we've got theta equals tan inverse of 4 minus 2. So we've got 2 points. This is x2, y2. And this is x1, y1. So tan inverse of 4 minus 2 divided by 3 minus 1. So tan inverse of the gradient. That's tan inverse of 1, which is theta is pi on 4, or 45 degrees. So if you're not really sure what this pi on 4 means, don't stress about it. When you get to circular functions, it'll start to make sense a bit more. But for now, you can use 45 degrees. Okay, so vertical and horizontal lines. So this is something people get quite confused by, especially when asked for what the gradient is for a vertical or horizontal line. So for a vertical line, it's expressed as x equals a. So you've basically got a line. So you've got y, you've got x, and x equals a, might be here. And it's basically parallel to the y-axis. So basically, regardless of your y value is, x will always equal to a. So if I was like x equals 1, and that's my vertical line, then whether y is negative 100, whether y is 0, x is still equal to 1. So this is an example of that line. So y can be 3, and x is still equal to 1. Y can be negative 6.67, and x is still equal to 1. So regardless of the y value, x is always equal to that constant. Now horizontal lines, so that's y equals b. So it's in that form. So basically you've got y, you've got x, and this could be the line. So y equals b. I know my drawing isn't perfect, but you want this line to be parallel to the x-axis. So regardless of what the x value is this time, y will always equal b. So whether x is 100, negative 1,000, y is always equal to b. So here's an example. So let's say y is equal to b. Here, if x was 10, y is still equal to b. If x was negative 10, y is still equal to 1. So here we've got y equals 1, and here we've got x equals 1. So hopefully that makes sense so far. Okay, parallel and perpendicular. Oh, actually something else I want to add about vertical and horizontal line. So people get confused about the gradient of these two lines. So this vertical line, think of it this way. So let's actually start with the horizontal line. So think of it as the slope of that line. Here, the line is so flat, it has no slope. So the gradient equals 0. So it's so flat that it has no slope whatsoever. That makes the gradient 0. Here, it's so steep that we can't even put a number to the gradient. So for this one, the gradient is undefined. So it's so steep that it's like we can't even assign a number to that gradient because of just how steep it is. So hopefully that's a good way of remembering for you. Okay, so now let's talk about parallel and perpendicular lines. So if you have a parallel lines, they basically have the same gradient. So they never intersect, and the gradients are the same. So the gradient of line 1 and the gradient of line 2 are equal. So for example, let's say we've got y equals 2x plus 4 and y equals 2x minus 3. You have the same gradient, so that 2. And that tells you that these two lines are parallel. Perpendicular lines, so basically they intersect at right angles to each other. So basically they are perpendicular. And for perpendicular lines, the gradient of that first line is the negative reciprocal of the gradient of that second line. So basically what that means is the gradient is negative 1 over the gradient of the other line. For example, y equals 2x plus 4, y equals 2x minus 3. So these are parallel, but to make them perpendicular, you go, not parallel, y equals, and the gradient is negative 1 on 2 x, and then plus any constant, plus c. It can be anything. Okay, so here parallel lines. So here's an example of parallel lines. So we've got y equals 2x plus 4, like in the example, and then y equals 2x minus 3. So you can see that they're perfectly parallel. They're never ever going to intersect. They're always the same distance from each other, and that makes a parallel line. So same gradient, different y-intercept means that they're parallel. Here, perpendicular lines. So we've got okay, so this is the perpendicular line, negative a half x plus 1. This is our original line, 2x plus 4. And we need to be aware that they intersect at right angles to each other. So really, really important concepts, and you'll be asked to apply these concepts this year, so in 1-2 methods and in 3-4 methods. If you want to find the equation of lines, so linear lines or just lines in general, you need 2 pieces of information. So you can either have 2 points on that line, you can have the gradient of that line and the point that lies on the line, or you could have the y-intercept and the gradient. So essentially that's still gradient and the point that lies on the line. You can use y equals mx plus c or y minus y1 equals mx minus x1. So this one is your actual equation. This is something that you can use to get to the equation. So I'll elaborate on both of them in a little bit of time. Okay, so linear equations, you can have 1, none, or infinitely many intersections. So I should clarify on this. I should say that let's say you have 2 linear equations. Those 2 linear equations, when you plot out those lines, you can have 1 intersection between those 2 lines. You can have no intersection between those lines, or infinitely many intersections between those lines. So if you want to have 1 intersection, all you want is that they're not parallel, so they intersect once at some point. 0 intersection means that you want them to be parallel. So you want M1 equals M2, but you don't want C1 equals C2, and I'll get to why in a bit. Infinitely many intersection means you essentially have the same line. So here you got M1 equals M2, C1 equals C2. So that's basically you have the same line. 1 intersection, you want M1 is not equal to M2. That's your condition here. If you have different gradients, there'll always be 1 intersection. If you have the same gradient but different y-intercepts, they'll be parallel, the lines will be parallel, and there'll be no intersection. And if you have infinitely many intersections, it means that those 2 lines are exactly the same. So the gradient is the same, the gradients are the same, and the y-intercepts are the same as well. Okay, so that's it for linear equation. If you need a break, you can pause, have a drink of water, stretch. But we'll just go straight to notation. So when it comes to 3-4 methods especially, notation is really important. And you need to, during 1-2 methods, it's important that you start to get used to the different types of notation that you need to use in methods. Okay, it's important, and it's also basically the language of maths. So it's sort of the language that you'll be using for your maths. So really important that you remember your notation and you know how to use it. So here we'll be looking at set notation, function notation. So basically how to represent a group of numbers and how to represent functions in maths. Keep in mind, a set is a collection of objects. So in maths, I guess, a set is a collection of numbers. These might be familiar to you, intersections and unions. So if you have an intersection, it's basically a set of elements that are common in 2 sets. So for example, so it's denoted by this, and it basically means and. So for example, if I say how many people play basketball and soccer, that and tells me it's an intersection. So you're looking at people who play both of those sports. If I ask about union, I'm basically saying or. So how many people play basketball or soccer? So it's like you can choose this or you can choose the other. It can be either of them. Excluding. So basically here we're basically saying how many people play basketball but not soccer. Here we're excluding people who play soccer. Another way I can exclude is I can say how many people play basketball but don't like playing basketball. So I'm excluding people who like playing basketball. So how many people play basketball but don't like playing basketball? And lastly, elementor. So this is basically if you have a set, you basically have stuff inside the set, so elements of the set. So for example, basketball and soccer are elements of sport. So they fall inside the set of sport. So they fall under the category of sport. So a Venn diagram is a really good way to visualize. So here is our intersection. So A is basketball, B is soccer. This intersection is something that falls into both categories, so basketball and soccer. Union, so this is union here. It can be A or B, doesn't matter. It includes just A, it includes just B, it includes the intersection as well. So when I say A or B, I'm talking about the union. And then excluding, we don't have a Venn diagram, but it's basically A not B. Element of, so if I had a little category inside A, then this little blue thing would be an element of A. And a little tip, set notation is really, really important when we talk about domain and range. So we're going to come to that towards sort of the end of our lecture, but just keep set notation in mind. There's some sets that are already predetermined. So what that means is they occur quite commonly, and it just makes sense to give them, sort of assign them a letter to determine what they mean. So for example, we've got n, which is natural numbers. So that's probably the smallest set out of all of these. And natural numbers are your positive whole numbers. It's sometimes 0. Again, it's a bit of a gray area whether it includes a 0 or not. But in methods, you're not really going to be using, you're not really going to talk much about natural numbers. Z, so Z is something that does come up. So Z is integers, so it's whole numbers, but this time it's negative and positive. So remember, natural numbers is just positive whole numbers. Z is negative and positive whole numbers. So these natural numbers is an element of Z. So natural numbers are an element of integers because they fall under the category of integers. Now we're getting bigger. Q is rational numbers. So rational numbers are numbers that you can express as a fraction. So as P over Q. So for example, a half is a rational number because you can express it as a fraction. But pi is an irrational number because it continues. There's no exact fraction that you can use to represent pi. Another example of a rational number is a third. So anything that you can write as a fraction. And lastly, you have real numbers. So real numbers is all rational numbers, all irrational numbers, all the numbers that you can plot on the number line. An example of a rational number, so you have pi, you have stuff like a half, you have 3, you have -3, so and so on. An example of a number that is not real, so something like square root of -1. So you can't have a square root of a negative number, that's not a real number. If you're doing spec, you're going to also have another category, a bigger one, with complex numbers and so on. But we don't care about that in methods. To represent a set of numbers, you basically use interval notation, or you can use this sort of brackets. So for example, to use these curly brackets, it's basically telling you particular values in that set. So if I say the set of even numbers from 1 to 10, I can use these curly brackets to do 2, 4, 6, 8, and 10. And if I use round or square brackets, so these are much more common. Round brackets, that's to indicate numbers that are up to, but excluding the endpoint. So if I say x is greater than 4, it's hard to use curly brackets. So it's hard to be like x is curly brackets 1.00001. Oh, sorry, not 1. 4.0001. 4.00. So there's just going to be so many numbers that are going to come up, and I can't possibly list them all. So we just say x is a subset of 4 to infinity, or x is an element of 4 to infinity. So basically, all I'm trying to say here is 4 to infinity are the values that x can take. These square brackets include. So they include that 4. The round brackets do not include. A little note, we never include infinity. Okay, so to make this easier to understand, I think it might be good to use, the greater than or equal to signs just to show what's happening here. So what this means here, is x is greater than or equal to 4 and less than infinity. So basically, x is greater than or equal to 4. What this here means is x is greater than 1 because it's a round bracket, so when it's not included, but less than or equal to 50 because it's a square bracket, that 50 is included. So that's basically how we're converting to interval notation. Okay. So this is greater than or equal to here. So to define a function, you basically need its rule and its domain. So this is the domain here. And the rule goes here. So your rule is the equation of the function. The domain is all the x values that the function can take. So a little bit of a summary. So this first f here, that is telling me that we are defining it as a function. So it's telling me that this whole thing is now being defined as a function. The AB is the domain. So function notation doesn't tell you the range, but by knowing the domain, by knowing what x values are there on the graph, we can figure out what y values are going to be there. And the y values are the range. The second R is called the codomain. So in methods, it's always going to be R. So don't worry about it. A common misconception is that people think that this R is the range. It's not. It's not the range. It's the codomain, always going to be R in methods. So you don't even need to bother about it. Okay, so f of x equals. So that's where we're getting the rule of our function. So here is our rule. So it's basically what process, so what do we need to do to x to get the y value? And if you're confused about what a function is, it's a good idea to sort of think about it as a machine. So you have your input, which is your x value, and then you have your output, which is your y value. And you put the x value through that machine. So here, for example, you're putting an x value, multiplying by 2, adding 1 to get the y value. So you put that x value through the machine, it goes through it, and you're going to get the y value. A few exam tips when it comes to function. When you're labeling the function and giving the name and giving the dependent variables, be really careful. So you can't just go from f of x equals ax plus b. You can't just go from there to y equals ax plus b. You can't just go straight from there. You actually have to put something in between, such as let y equals f of x or something like that. So you can't just go straight from the first, so from this function equation to just y equals. So that's something to look out for. And it's something to look out for when you're doing inverse functions. And second thing, look at marks to see if domain is required in your answer. So sometimes people are questions are like, write the rule of the function or find the rule of the function. So when you're asked that, you just need to write the rule. You don't need to write your domain or anything. But if it says something like find the function of f of x or find f of x, if it asks something like that, it's most likely that you're going to have to write the domain as well. So if it says find the rule or anything about just the rule, then you just need the rule. But if it just says find, then you'll most likely have to write the domain as well. So the best way to know whether you have to do it or not is just look at your marks. So look at how many marks there are. Okay, so that's an introduction to function notation. If a function has to exist, then the rule must pass the vertical line test. So this vertical line test is not a huge part of the study design anymore. So it's not going to be tested, but it's good knowledge to have to decide whether something is a function or not. So sometimes if the function doesn't pass the vertical line test, we might have to restrict the domain. So we'll talk about that a little bit more later on. Essentially, for a function, every x value should have its own unique y value. And we use the vertical line test to check this out. So for example, let's see these two. Vertical line test, intersects only once. Vertical line test, intersects only once. So at any point on this graph, if you draw a vertical line, that vertical line is only going to intersect once. So this tells me that the function, so this is a function. Here, if I draw a vertical line, here at this point, it intersects once, but every other point on the graph, it intersects twice. So here, this is not a function. This is a function here. So you use the vertical line test. If it intersects more than once, it's not a function. Simple as that. So even if it intersects once here, at any point, if it intersects more than once, it's not a function. That's it. Okay, so that's it for functions. We'll come back to more functions. So there is still more content on functions. But let's go through some of the graphs that we might need to have a look at. So firstly, quadratic. So hopefully this is just revision for most of you. So quadratic is basically an equation and it has the degree x squared. So it has a degree of 2. So the highest power is 2. So degree. So if a question ever asks you for the degree, don't write degree equals x squared. Here the degree is 2 because it's just a power. So a quadratic is a polynomial of degree 2. The general form of a quadratic function is here. So it's all real numbers because it can take all x values from this way and this way. So it goes forever to the right, goes forever to the left. And the rule, so this is the general rule. The rule is ax squared plus bx plus c. So that's your rule for a quadratic. So there's quite a few ways that you can write your quadratic rule. So you can write it in your turning point form. So for example, a times x minus h squared plus k, and your turning point is hk. So let's write that on our graph. hk, okay. We can write it in our factorized form. So we can have it like this. So a times x minus m, x minus n, and then the x-intercepts are at m0 and n0. So this is the factorized or intercept form. So this is useful to give your turning point. This is useful to get the x-intercepts. And lastly, this is useful for y-intercept, because y-intercept is 0 and c. Okay, so to continue, if you want to find the x-intercept of a function, we use the null factor law. So remember, we want it in the intercept form. So a times, so y equals a times x minus m, what else? X minus n. So that's our intercept form. And the null factor law tells us that so remember, to find the x-intercept, y has to be 0. And the null factor law tells us that if we're going to get an answer of 0, either this has to be equal 0, this has to equal 0, or both of them are equal to 0. So x minus m equals 0, or x minus n equals 0. So if we were to find the x-intercept for this, we say either 1, x minus m equals 0, and x equals m, or we can say x minus n equals 0 and x equals n. So you can write it either way. When you write quadratic equations, they come in quite a few forms. So I've touched on this earlier, but let's just reiterate. So turning point form, best for finding the turning point of the graph. X-intercept form, or the intercept form, or the factorized form, so it could be called using any of those names, is written like this. And this is most useful for finding the x-intercepts. So for example here, m0 and n0 are your x-intercepts. And writing it in this form makes it really useful to get those x-intercepts. And lastly, you have the general form. So general form, so you write it as y equals ax squared plus bx plus c. This is most useful for y-intercept. So y-intercept is 0 and c. Okay, so moving on from the general form, we'll come to the quadratic formula. So the quadratic formula helps us find the x-intercepts without having to factorize. So without needing to go from here to here, you don't need to do that. You can just use quadratic formula to find your x-intercepts. Okay, so let's say you have an equation. So ax squared plus bx plus c, so that's your expression. To find the x-intercepts, you just substitute it into the formula. So negative b plus or minus square root of b squared minus 4ac divided by 2a. So I think most of you would have heard what the quadratic formula is, and I think the majority of you would also know how to apply it. Few exam tips. So it's usually faster to factorize. So it's a good idea to just factorize if the quadratic equation is quite easy. If there's a hard quadratic, so if you have very complicated numbers and you look at it and you're like, it's probably going to take me a long time to factorize this, that's when you should use the quadratic formula. Again, formula not in the formula sheet, so something to memorize. And when you're subbing A, B, and C, just use brackets. So to avoid any confusion with the negatives, make sure that you use brackets. And remember, be mindful of the sign. So be mindful of the sign in front of these, and when you're substituting, keep the sign as well. So that's it for quadratics. So continuing from the quadratic formula, you need to know about the discriminant. So discriminant is something that helps us find how many solutions a quadratic has. So let's say we have a really complicated looking quadratic equation, and it's like, how many x-intercepts does this quadratic have? Instead of trying to use the quadratic formula and solving for the x-intercepts and spending a lot of time on that, it might just be easier to use the discriminant. So discriminant tells us how many solutions the quadratic has, and it's written like this. So really important thing to remember. So 3 options. If the discriminant is greater than 0, there are 2 solutions. If it's equal to 0, there's 1 solution. If it's less than 0, there is no solution. And it's derived from the quadratic formula. So I will just highlight where it's coming from. So it's this part of the quadratic formula. Okay, so let's relate our knowledge now. So let's figure out why it happens this way. So what's happening here, b squared minus 4ac, if this thing inside the square roots, so if this thing inside the square root is greater than 0, it means square root greater than 0, square root of a positive number, you're going to have a positive and negative solution. So it makes sense that there are 2 solutions. If this thing inside the square root is equal to 0, it makes sense that you have 1 solution, because square root of 0 is just 0. And it doesn't matter if it's positive or negative. Minus b plus 0 is the same thing, minus b minus 0 is still the same thing. So that's why you have 1 solution. And if it's less than 0, so the thing inside the square root is less than 0, it means that you have a negative inside your quadratic. So that's really problematic because you can't square root a negative number. So in that case, you have no solutions. Oh, actually, before I keep moving on, I just want to show you how it looks on the graph. So if it has 2 solutions, it will look So you've got y, you've got x. It'll look something like this. So it's intersecting with the x-axis twice. If you have one solution, it means that the solution is on the turning point. So it's going to look like this. So you've got y, you've got x. To have one solution, orthograph, imagine this is a quadratic. If you have one solution, then that solution is on the turning point as well. And lastly, no solution, that's going to look like this. So you've got y, got x. It's not going to touch the x-axis. It's not even going to touch the x-axis. It's not going to intersect the x-axis. So that's how you do this. And I think it's a good idea to sort of visualize those graphs, because knowing how many solutions there are will give you a rough idea on how the graph might look. Okay, so now to inequalities. So in linear equations, in a linear equation, it's quite easy to figure out our inequalities. So you can have something is greater than, so let's say A is greater than or equal to B, greater than B, or less than B. So 3 ways, or 4 ways, less than or equal to. So remember, people do sometimes tend to get confused by which side the sign should face. So the open end should face the bigger one. So here, open end facing A, which is bigger. When you have linear inequalities, pretty straightforward. It's almost equivalent to just solving an equation, so solving for something with an equal sign, except if you multiply or divide by a negative number. So if you multiply or divide by negative, you have to flip the inequality sign. So for example, let's say A is greater than B. Negative A is less than negative B. So if you want to know why that happens, let's say A equals 2. Actually, let's say A equals 5 and B equals 1. It makes sense that negative 5 is less than negative 1. So we know that 5 is greater than 1, but negative 5 is less than negative 1. So just using that logic. If you have complicated functions, you have some interesting behavior. So let's say you have a quadratic. To know where the x value lies and what it's between, it's important that you are aware of the graph. So it's hard to just do it in your head without visualizing it. So when you deal with linear inequalities or linear inequations, you can just solve it straightforwardly. So just use algebra, solve it like you would solve an equation. Just remember to flip the sign when multiplying or dividing by negative. But when you're doing nonlinear equations, you can't really do it straightforwardly. And the best thing to do is just solve it graphically. So draw a graph, and using that graph, sort of visualize it and solve it that way. So now let's move on to our next slide. So this time we're coming back to functions. So this time we're going to be working on rational functions. So basically rational functions are any function that you can write as a fraction, and you want the numerator and denominator to be polynomial. So you want them to have positive whole number powers. So just a sum of x's raised to integer powers. So an example is 2x cubed plus 2x minus 5 on 2. That's a great example of a polynomial because it has positive powers. So x to the power of 3, x to the power of 1. An example of a rational function. So you've got x squared on top. So you've got a polynomial on top and a polynomial on the bottom. Another example. This is also a rational function because technically you've got 2x to the power of 0. So polynomial on top, degree 0. And polynomial on the bottom with a degree of 2. So because you have a denominator with x's in it, sometimes there's a few issues when you're trying to figure out the domain of a polynomial, of a rational function, sorry. So keep in mind, you can't have any number divided by 0. So that's equal to no real numbers. So you can't divide by a 0. So let's say you've got a function of 1 on x minus 2. When x is 2, we're going to have 1 on 0. Okay? And how is it possible? It's actually not possible. You can't do 1 on 0. So what that means is, for this function, x cannot equal 0. So in the domain, you're going to say x is all real numbers except 0. So remember we talked about the backslash, meaning except. So you're excluding something. And the curly brackets indicate that you're excluding something specific. Except, 2 here, because x can't be 2. Because if x is 2, the denominator is 0, and that won't work out for us. So to avoid this division by 0, we make sure that the domain excludes any values of x that give us any issues. So like we did before here, so if f of x is p of x divided by q of x, then we say the denominator is not equal to 0, and then we solve for x. So for example, if we have f of x equals 1 on x plus 3, this is the denominator, and we say x plus 3 is not equal to 0, therefore x is not equal to negative 3. And that's what we're putting in the domain. We're excluding that negative 3 value. So lucky for us, in methods, we only have 2 families of rational functions that we need to deal with. So you basically have hyperbola, which are basically, so this is the base functions, just 1 on x, and then you just transform it. So you add your translations, move it up, move it down, move it to the right, move it left, stretch it, squish it. So that's what's happening. But essentially, this is your base function. So for example, if we have this function, so 2 on x plus 1 plus 2, we know that the domain is all real numbers except negative 1. Because if x was negative 1, the denominator would be 0. Our second family is trunca or truncus. So that's basically a transformation of this base function. So f of x is 1 on x squared. So here you've got f of x, let's say 3 on x minus 1 squared. Again, denominator can't be equal to 0. So we have to say x minus 1 squared is not equal to 0. So therefore, x is not equal to 1. So again, domain is all real numbers except 1. So let's talk a bit more about the function. So just ignore the graph for a bit. I know that it looks a little bit complicated. The most common form for the hyperbola is just 1 on x. So we know that x is not equal to 0. And there's no way that y can be equal to 0 as well. So there's no way the y value can be equal to 0. Because 1 on 0, no real numbers. And any number other than 0, so 1 on any number that's not 0, is going to give you a number that's not 0. So x is not equal to 0, and y is not equal to 0 either. These lines, so x equals 0, y equals 0, so these lines are actually called asymptotes. And you might have heard this term before. Asymptotes basically means that it's a line that the function gets close to, so it's getting closer and closer and closer to that function. So the function is getting closer and closer and closer to the line, but it just never touches that line. And that's because you're getting close to 0. So let's say we do 1 on, so let's say we do x equals 1. 1 on 1 is 1. Let's say we do x equals 2. 1 on 2, getting closer to 0. So if we're going this way, x is 2, getting closer to 0 again, because f of x is a half now. Let's say x equals 10, f of x is 1 on 10. So it's getting closer and closer and closer to 0. If x equals 1000, f of x is 1 on 1000. So you're getting close to 0, but you're never going to actually touch that 0. So now let's move on to general form of a hyperbola. So this is something really important to remember. So to save you time, x equals h, we've got an asymptote. Y equals k, we've got another asymptote. And this a tells you your dilations. So how much the graph is being squished or stretched. When you write your asymptotes, don't write it as x is not equal to h or y is not equal to k, because the equation of the asymptote is x equals h, y equals k. So make sure that you don't have those the unequal or the not equal signs when you're writing those asymptotes. So the equation of the asymptote, x equals h, y equals k. So let's do an example here. You might want to pause this and have a go at it by yourself. So on the axes, sketch the graph. Okay, all real numbers not equal to 1. F of x equals 2 minus 4 on x plus 1. Label all axes intercepts, label each asymptote with its equation. Okay, perfect. So remember, y equals a on x minus h plus k. And then the asymptotes are x equals h, y equals k. So here, the asymptotes. So that's the first thing. X equals -1, y equals 2. In a positive graph, so if we've got y equals 1 on x, it's going to look like this. So we've got y, got x, like this, like this. Oh, not a good graph here. But it's going to look something like this. If we have y equals -1 on x, it's going to look like this. So y, x, up. So that's something to keep in mind. Here, we've got negative. It wants us to label axis intercepts as well. Okay, cool. So first, I'm going to put my asymptotes in. So I want to make them very, very clear. So I'll do it in red because those asymptotes are probably the most important part of my graph. So when we draw asymptotes, we use a dotted line to show our asymptotes. So for example here, y equals 2, x equals -1. So let's do x equals -1 first. Might be here. Okay, and label them. So x equals -1. And then we've got y equals 2. Probably something like this. Here we've got y equals 2. Perfect. So those are our asymptotes. Okay. We've done our asymptotes. Perfect. Now let's find our axis intercepts. So remember, x-intercept, y equals 0. So 2 minus 4 on x plus 1 equals 0. Minus 4 on x plus 1 equals -2. X plus 1 equals 2. X equals 2 minus 1, which is just 1. So our x-intercept is 1, 0. Okay, cool. Let's find our y-intercept. I'll do it here. So y-intercept, x equals 0. So y equals 2 minus 4 on 0 plus 1, which equals 2 minus 4, which equals -2. So the y-intercept is 0, -2. Okay, perfect. A little sneaky trick I like to use. I like to draw the graph before I actually label the intercept, because sometimes I might not draw them perfectly of the intercepts. Okay, so we've got x-intercept of 1, 0, y-intercept of 0, -2. Okay, so let's draw it. It's a negative here, which means it's going to look like this. So let's draw the graph. We want to show that it is approaching, moving away, and approaching again. And these arrows to show that it is continuing forever. Okay, I'll label the intercepts now. Here you've got 0, -2, 1, and 0. Okay. I know it sounds really obvious now, but don't forget to draw the other half of the graph, because there's times when I've seen students be so stressed out with the exam, be so stressed about the time, that sometimes people just actually forget to draw that second part. So make sure you remember to do that. Don't lose marks that you actually can gain so easily. So the other side of the graph, again, show that it's approaching away and keep drawing it. Okay, and that looks good. So that's how you would draw it. Few tips. Axes, intercepts, they're coordinates, so don't just write -2 and 1. They're coordinates. So always give your axes, intercepts, no matter what graph it is, give them as coordinates. Here, these arrows at the end of the graph, I think they're optional, but so my teacher always marked me down for not showing those arrows. So I just got in the habit of writing them. And it's these teachers who are going to be marking the exams and your SACs. So you might as well get into the habit of doing it the way that, so just being as safe as possible. So I'd advise drawing the arrows. But yeah, that's how you would draw a hyperbola. Another worked example. So this one's a little bit more tricky because it's not in this form. So it's not in the form y equals a on x minus h plus k. So it's not in the form that we want, and that makes it really difficult for us to draw the equation. So to draw the graph, sorry. So to make this look like this, we just use our logic. So we've got y equals x plus 2 on x plus 1. Well, that's the same as x plus 1 on 2. It's still x plus 2. Oh, sorry, x plus 1. So this thing on the bottom is the same as what's on the top. So x plus 1 is just x plus 2 on x plus 1. So we haven't really changed anything. Let's split it apart. So that's equal to x plus 1 on x plus 1 plus 1 on x plus 1. So we're splitting this and we're splitting this. That's equal to 1 on x plus 1 plus 1, because x plus 1 and x plus 1 cancel out to give you 1. Okay, now to find our asymptotes. So asymptote x equals -1, because x can't actually equal -1, and y equals 1. So now we've got our form, we've got our asymptotes. Okay, let's get the graph up. So I'll use a different color to make it very, very obvious. So we've got vertical, y-axis, y, we get horizontal, x-axis. Okay, and let's put in our asymptotes straight away. So x equals -1, probably around here. So x equals -1, y equals 1, yeah, around here. Okay, great. We've got our asymptotes. Now let's find our axis intercepts. So to find the x-int, so the x-intercept, y equals 0. So go 1 on x plus 1 equals 0. 1 on x plus 1 equals -1. X plus 1 equals still -1. X equals -1 minus 1, -2. So our coordinates are -2, 0. Next, let's find the y-intercept. So y-int x equals 0. So we've got 0 plus 2. So y equals on 0 plus 1. That's equal to 2 on 1, which is just 2. So the coordinate is 0, 2. Okay, so now let's draw the graph. Again, I'm just going to draw the graph first and label the intercept later. Oh, okay, I'm going to have to erase that. That's not acceptable at all. Okay, try again. So continue. Ideally, when you're drawing this on paper, you don't have that weird bump. Here, label the coordinates, so that is 0, 2. And then next, the negative graph. Approach and stop. So if you feel like you're going to touch the asymptote, stop. Before you touch it, just stop, draw the line, and that's fine. And this is -2, 0. So here we go. So that's basically how you would draw this graph. Are we showing all intercepts? Yes, we are. Are we showing your asymptotes? Yes, we are. Is that curve smooth? Yeah, reasonably. When you draw this on paper, it will be much easier. Okay, so that's it for hyperbolus. Let's go to truncus. So the most common form of a truncus is f of x is 1 on x squared. And it's always positive. So you don't have, unless you have like a negative in front of it, it's not going to be below the below the x-axis, sorry. It also has asymptotes. So for this one, it has an asymptotes at x equals 0 and y equals 0. So similar asymptotes to a hyperbola. So here's what it looks like. So you've got asymptotes, so horizontally, and you've got vertical asymptotes as well. It has a general formula, so you've got f of x equals a on x minus h squared plus k, and you've got an asymptote at x equals h here, and y equals k here. And keep in mind, same as before, that a is your dilation, so squish, stretch. If a is negative, it means it's reflected. A few exam tips. So when you sketch asymptotes, make sure you use that dotted line, use a ruler. And even if the asymptote is on the axis. So for example, if you have something like this, so let's say you've got y, you've got x, and your graph is y equals 1 on x. Your asymptotes are y equals 0, x equals 0. So when you're using a pencil and you're drawing on that black line, it might be hard to see the asymptote. So what I like to do is I like to draw it slightly to the side so you can see the markings I made and label it clearly. So x equals 0, and then slightly to the x side, extend it a little bit more so it's very easy to see that you've drawn an asymptote, and here you've got x equals 0. Okay, so use that dotted line to sketch an asymptote, and never let your graph touch the asymptote, because you know that if your graph touches the asymptote, you've drawn it wrong. So always approach it, so get closer and closer and closer to the asymptote, just never ever touch. Okay, so that's it for truncus. Let's do an example. Actually, I think it might be a good idea. I'll just make up an example now. So let's do a simple one. So if you know how to draw hyperbolus, you know how to draw truncus. So the principles are essentially the same. Okay, so let's do y equals 2 on x minus 1 plus 1. Okay, so we've got y, got our x. Okay, use this. Okay, so our asymptotes, x minus 1. So we've got an asymptote at x equals 1. And then we've got another asymptote at y equals 1. Oh, sorry, this is y equals 1. We've got an asymptote at x equals 1, which is probably around here. Asymptotes and the truncus will look like this. Approach the asymptote, and same on the other side. Okay, if you have a negative graph, so let's say we've got y equals negative, so we've got y equals 1 on x squared. That looks like this. X, y. It's gonna go look like that. So again, these graphs are not perfect. I just want to show you the position of the graph. That's it. So I'm not trying to show the shape of the graph, or I'm not trying to make it accurate here. I just want to show you the position. If you've got y equals 1 on negative 1 on x squared, your graph is going to be reflected. So you've got y, got x, going to be like this now. And that's it. Okay, so next concept is square root functions. Square root functions are basically a function, as the name suggests, function inside the square root. So for example, you've got f of x is square root of x. It's unidirectional, it starts at 0, 0. So I'll show you an example of how it looks. So we've got y, x, you've got an endpoint at 0, 0. And it goes like this, one direction, just on the right. And the reason is we can't square root negative. So you actually cannot have a square root on this side because you can't do square root of negative values of x. You can square root 0, so that's why you have this 0, 0 starting point. So essentially our domain is x is greater than or equal to 0. So x is from 0 included to infinity. If you have f of x is this, so this is our general form. So this is our general form. We say x is greater than or equal to b because x minus b greater than or equal to 0. And the start point is BC. So these are our starting point, BC. But if you have f of x is negative square root of x, so negative, so square root and then inside negative x, then negative x is greater than or equal to 0, which means x is less than or equal to 0. So the graph will look like this. So we've got y, we've got x, go, and this way. So that's the way it's going to look. So essentially here, if you have a positive x value, so if let's say x is negative, if x is 4, you can't do square root of negative 4, but you can do square root of negative 4, which is just square root of 4. Okay, so again, back to the general form. HK, that's our endpoint of the square root. And they're also horizontal and vertical translation. So the endpoint can move up, it can move down, it can move to the right, it can move to the left. If a is less than 0, the graph is reflected over the x-axis. If b is less than 0, it's reflected over the y-axis. Okay, so let me just draw a graph to show you what's happening. So we've got y, got x, and I'm just going to use different colors to save time. So let's start with our basic graph. Starts at 0, 0, so all of the graphs are starting there and going this way. So this is y equals square root of x. So and it's going 0, 0. You've got another graph. Let's say you've got the graph this way. This is y equals square root of negative x. So we talked about this earlier. Another graph. So let's do it purple. So they're all starting here. Here, this is y equals negative square root of x. And lastly, we've got, let's go green. Here we have y is negative square root of negative x. So that's how we draw these graphs. So hopefully it's straightforward. You can see sort of the pattern of what's happening. Okay, square root, that's it. So circles, circles aren't a huge part of 3-form methods. They might come up just sort of like general knowledge, but it's not really a big part. The general rule for a circle is this. So you've got origin of 0, 0. So starting at the center. R is the radius of the circle. So how big is the radius? So here we go. So this is the length of R. Your origin here is 0 and 0. And your radius, yeah, is 1 here. So you can see this equation. 1 squared, that's a radius. The general equation for a circle, so HK, that's your origin, or that's sort of your center. And R is still the radius. Oh, this is wrong. It should be equals R squared. Okay, sorry about that error. It should be equals. So r is the radius of the circle. So remember, r squared is not the radius, it's just this r that is the radius of the circle. Okay, so that's it for circles. It's not a big part of the study design, so I don't think there's much point in going through them in depth. So let's go to domain and range. So these are really, really big parts of the study design. So domain of a function, so that's the set of the x values that the function will work with, so that the function can actually take. So it's your input of that function. And the range is your output. So basically, depending on what x's you put in, what is the output of the function. So all the y values that you could possibly get with that function. So if the function is f of x equals x squared, the domain is r and the range is 0 to infinity. Okay? Always a curly? No, always a round. 0, so you've got y, you've got x squared, so like this, something like that. Okay, so x can go either way forever. So it can go negative infinity, positive infinity, forever. But y starts at the turning point of 0, 0. So it includes the turning point and then goes up forever. It doesn't go down. So that's why the range is from 0 included to infinity. And make sure that you remember, infinity always has a round bracket. So negative infinity is round bracket. Infinity, round bracket. So keep that in mind. Sometimes we get rid of this part of the function and only write the rule. And that's because the domain of that function is sort of implied. So if I tell you here f of x is square root of x, well, the domain is implied. It's implied that it's from 0 included to infinity. The maximal domain of a function, so that's a word that you hear quite often, so maximal domain. And that's basically the largest set of x values where the function actually exists. So what x values does the function exist? So let's talk about the quadratic before. So if you have f of x equals x squared, then x is a subset of all real numbers because x can exist for any x value. But if you say f of x is a hyperbola 1 on x, then x is a subset of all real numbers except 0. So based on that equation, what values can the function exist for? So that's your maximal domain. So let's do an example. So find the maximal domain and the resulting range of the following. Here, it's a good idea if you want to pause and have a go at it yourself, but I'll just get onto it. So f of x is square root of 3x minus 2. That's equal to square root of 3x minus 2 on 3. So the starting point, so your square root graph will look something like this. So starting point is maybe here. So 2 on 3 and 0. Go up like this. Okay. So here we can see the domain. So the domain of function f equals 2 on 3 to infinity. So keep in mind it's a square bracket because we're including that endpoint because it's a closed circle. We're including that endpoint. Okay, so now the range of f equals, so it's starting from 0 to up. It's going up forever. 0 to infinity. Another way you can write that is all positive real numbers union 0 including 0. So you can write it either way and you'd still be correct. Another example. So for this one, again, you can pause if you want to have a go at it. So now's a good time to pause. So to do this one, you want to find the maximal domain. So you've got f of x equals square root of 1 minus x squared. To find the maximal domain, let's rewrite it into a formula. So f of x equals negative, no negative, square root of negative x squared plus 1. Okay, so this is a bit more tricky. Negative x squared plus 1. Negative x squared plus 1 should be greater than or equal to 0. So how does this graph look? Well, you got your y, got your x, y-intercept of plus 1, and negative, so it's going to go this way, going to go this way. And we want negative x squared plus 1, we want that graph to be greater than or equal to 0. So from here to here is what we want to include. So these points, so this is negative 1, 0. This is 1 and 0. So those are our endpoints. And so the domain of this graph, x, is from negative 1 to 1. So the domain of this function is negative 1 to 1. So it's a smaller domain here. So again, this is a little bit trickier, but essentially you want to see when the inside of this is greater than or equal to 0. And it's greater than or equal to 0 for this interval, so above the x-axis, and for this domain. So that's how you'd figure out the domain for this one. Okay, so now we're up to sort of the last part of the lecture. So this time we're going to be talking about inverses. So when you do inverses, it's a good idea to follow the specific process. So there's like a very straightforward process to use, and when you follow it, you're guaranteed to get the marks. So let's say you've got y equals f of x. If you're given x, then you can easily find y. So you can easily find y equals f of x. So if you're given y equals f of x, which equals 2x plus 3, and x equals 2, you can say f of 2 equals 2 to the power of 2 plus 3, which equals 3, which equals 4 plus 3, which equals 7. What about the other way around? So if you get a y, can you find the x? So that's the point of the inverse function. So it's basically to reverse the original function and sort of invert or swap x and y. A key condition is the function has to be 1-to-1. So we're coming back to the vertical line test. So what it means for a function to be 1-to-1 is I draw a horizontal line, it should only intersect once. I draw a vertical line, should only intersect once at any point. So here, this function isn't 1-to-1. So here, vertical line intersects once, but horizontal line actually intersects twice. So it's not a 1-to-1 function, and that's where we get issues. So we need to restrict the domain to make it 1-to-1. So for example, let's do the quadratic again. Got y, got x. Let's restrict the domain. So this is, perfect graph. 0, 0. So this is 1-to-1. Because if I draw a vertical line, intersects once, horizontal line intersects once. So my point is that if you have a function that's not 1-to-1, you can always restrict the domain and make it and force it to be 1-to-1. Okay. So a few key properties of inverse functions. So firstly, f and f inverse. So they're related by a reflection about y equals x. So let's say you've got, let me illustrate that. So y got x. Let's say this is our original function. This is the line y equals x. The inverse function will look like this. So it's reflected. And they also intersect along that line. So they intersect only along that line. And the domain and range swap. So this is a really useful property. So the domain of the original function becomes the range of the inverse function. And the range of the original function becomes the domain of the inverse function. So that's because you're swapping x and y, so you're also swapping the values of x and y. So the steps to do it: first, you have to write y equals f of x, or let y equals f of x. Swap x and y. So you have to say to find inverse, swap x and y. And then rearrange to make y the subject again. And then I should write a number 4. Write f of 1 of x equals, and write it. So don't just leave it as y equals something in terms of x. Oops. Oh, let's not go there. So find the rule for the function. So let's actually find the rule for the inverse. So let's say h of x equals 2x cubed plus 1. Find the rule. So it's just asking for the rule. It's only 2 mark. So we don't need to give the domain or anything. Find the rule for the inverse function h inverse. So let's do it. So first I'm going to do let y equals 2x cubed plus 1. Or which equals h of x. Or you can say let y equals h of x. You don't need to even write all of that out. Next, to find inverse. So I can write out inverse, or to find h inverse. Actually, I won't write that. I think it's better to just write to find inverse. So to find inverse, swap x and y. Okay, so that will help us find the inverse. So therefore, x equals 2y cubed plus 1. 2y cubed equals x minus 1. Y cubed equals half of x minus 1. And then go other side. Y equals half of x minus 1 to power of a third. So that's 1 on cube root of 2 x minus 1 to the power of a third. So I can write it like that. Okay, but we're not done yet because we want to find the inverse function h inverse. So we can't just leave it as y equals. We have to say h inverse of x equals 1 on cube root of 2 x minus 1 to the power of a third. And that's how we find the inverse function. So let's see the marking. So just over half the people got this correct. And you can see that it's not too hard to get those marks though. Okay, so let y equals 2x cubed minus 1, we've done that. For inverse, swap x and y, we've done that. Make y the subject like this. Yeah, we've done that. So we've gotten all those marks. And the guide itself says, the report itself says that you're not supposed to proceed directly from this to this. So you can't just go directly. You need that for inverse swap in x and y. Okay. A common error. So this is a common error. And obviously, we can't write it like this. So we have to have your function in terms of x. So you can't write h inverse of x is something in terms of y. Not going to work out. Okay, so that's basically the process of finding inverses. And it's pretty much the same for every graph. Let's do another example. So this is from a VCE exam, exam 2 from 2014. You've got a function. Okay, they've given this is the graph. So they don't give the graph, but it's a good idea for you to draw the graph yourself. It's just more convenient. And it will have an inverse function for what values of d. Okay, so basically what domain will give an inverse function for this. So what you have to do here is you have to see when the function is 1 to 1. So you have 3 scenarios. So first scenario, from here to here, a 1 to 1 function can exist. So you've got d equals negative infinity to negative 4. We can include 4. Our second scenario is maybe from here to here. So here d equals so include 7 to infinity. So here again, it's a 1 to 1 function. And lastly, you can have this middle part. Here, d equals -4 to 7 included, and that's it. Okay, so the reason that I'm splitting the graph like this is because it will only have an inverse function if it's 1 to 1. So remember, 1 to 1, when you draw a vertical line, should only intersect once. When you draw a horizontal line, should only intersect once. So that's the point of a 1 to 1 function. Okay, so it'll have an inverse function for, let's see which of the values correspond. So -infinity to -4. No, that's nowhere. Okay, fine. -4 to 7. That's nowhere. Okay, we can't do that. Next, 7 to infinity. Yep, this will work out. Perfect. So even if it doesn't include that 7, it's still, like, this is still a subset of this domain. So it still works out for us now. So the answer here is B. And only 55% got it right. So you can see that it's not important not only to, I guess, memorize the concept, but to actually understand it and apply it. Okay, so let's do another question. So let f be all reals except 0. Okay, f of x, okay. Find the inverse function. So remember what I said toward the start. Find f inverse. So it's not saying find the rule of. So look at the difference between this rule and this one. So here it's asking you to find the rule, but the wording here is different. Find the inverse function. So here you're going to have to include the domain. And you can see the marking. There's also more marks here too. So it makes sense. Okay, so let's do it. Same process as before. Here, pause. Have a go at the question and then listen to the recording again. So let's do it. So we've got f of x is 3 on x minus 4. So let y equals f of x. Oops. Okay, let y equals f of x. Therefore, y equals 3 on x minus 4. To find inverse, swap x and y. So therefore, 3 on y minus 4 equals x. So we've just swapped x and y. Now let's do 3 on y equals x plus 4. Y equals 3 on x plus 4. Okay, perfect. And now we can't just leave it like that. We need to find f inverse of x equals 3 on x plus 4. Okay, that's all well and good, but it's asking find the inverse function of f. Remember, the domain of the inverse equals the range of the original function. And the range of the original function is from all real numbers except -4. Okay, so drawing on our knowledge of hyperbolas, we can say the range of this function is all real numbers except -4, because the asymptote is at y equals -4. So therefore, the domain of the original function equals all reals except -4. Now, you'd probably get the marks if you leave it like that, but just to be safe, let's put it all together. So let's find it. Let's actually find the function. So let's define it. Oops, not like this. F inverse, define it. The domain is all reals except -4. Codomain is R, always R for methods. And then F inverse x equals 3 on x plus 4. And that will get us the marks that we want. So let's have a look at, I don't have the solution for this. Okay, you can always check out the VCA website to find who got it right. Okay, Oh, actually, here. Only 30% got it right. Few students realize that the rule and domain need to be specified. And the definition of F should be provided. Okay, so basically what's happening is a lot of people lost marks because they didn't get the domain. That's what it's saying. So you can see that it's pretty easy to get full marks. You just need to be very wary of the questions they're asking you. Okay, so a few things to remember. When we find the inverse functions, they're reflected on the line y equals x. So that will help you think about how the graph might look. And we can also say we swap the values of x and y. So basically, if they already give you a graph and it's asking you to just draw the inverse function, you don't need to do all this algebra. You can just visually try to do it by reflecting it on the line y equals x. Or if you're given the equation, you can always use algebra to swap x and y like we've been doing so far. So domain and range swap over, because we're swapping the x and y, we also swap the domain and range. So that definitely makes sense because just logically, when we swap x and y, we swap the domain and range. So essentially, if you have the point AB on the original graph, so the original function, then the inverse, it will be swapped, the x and y swap, and it will actually be BA. And another key thing that people forget, so f of f inverse of x is just x. So let's have a go at this one. Okay, so first part, find g of x. G of x equals f of x. Okay, doesn't matter. So g of x equals f of 1 on x squared. So f of x is basically where there is an x, we're putting the whole function in. That is 1 on x squared, which equals 1 on x to the power of 4. That's equal to x to the power of 4. Okay, perfect. And remember, domain is all positive real numbers. Evaluate g inverse of 16, where g inverse is the inverse function of g. So I'm assuming this is an exam 2 question because it's only 1 mark. Okay, g inverse of x. So first, let y equals g of x. Therefore, y equals x to the power of 4. Swap. Oops. Okay, swap x and y for inverse. Therefore, y to the power of 4 equals x. Y equals the 4th root x. Okay, so this is positive. So this graph would look something like all positive real numbers, x squared, like something like this. So the range of this is, not including 0, 0 to infinity. Okay. Okay, so here we can say g inverse of x equals, we don't even need the domain actually. I don't know why I did that. Okay, g inverse of x is 4th root of x. Therefore, g inverse of 16 equals 4th root of 16 is 2. And it's positive value because it's the positive domain. So hopefully that makes sense so far. Keep going. Again, reiterating what we've done so far. So inverse functions are reflected along the line y equals x. If you have an intersection between the original and inverse, it's going to occur on the line y equals x. So instead of going f of x equals f inverse of x to find the intersection, you can just do f of x equals x for the intersection. So it's just a shortcut to make your life a lot easier. So that's why you can just do f of x equals x or f inverse of x equals x, whichever one is easier. So that will keep it really clean, won't make it messy or anything. So let's do another question. So we've got a cubic function defined by this. Write the expression for the inverse. Okay, beautiful. Write an expression. So it's just a rule. Okay, so let y equals 3 minus 2x cubed to find inverse. So to find inverse, swap x and y. So when you swap x and y, you've got 3 minus 2y cubed equals x minus 2y cubed equals x minus 3. Y cubed equals x minus 3 on negative 2. Y equals cube root of x minus 3 on negative 2. Okay, so therefore expression for q inverse of x equals cube root of x minus 3 on negative 2. And that's how we would solve this one. So here we go. Yeah. Okay. Beautiful. Yeah. So we've done it correctly here. A lot of people got it right, which is great. It means that, it was a relatively easy question. Here are some of the few errors as well. So the examiner report. So the exam report is actually a really good resource, because when you do an exam and you're correcting it, it's actually telling you what to look out for, or the common mistakes that are made that you should try not to make in the future. Okay, next, the points of intersection between the graphs q of x and q inverse of x. Okay, so what was q of x? Q of x, 3 minus 2x cubed. So q of x was 3 minus x cubed. The points of intersection. So to do this, it's actually easier to go 3 minus 2x cubed equals x. Solve. So 2x cubed plus x plus 3 equals 0. You can solve using your calculator, because I'm pretty sure this is going to be a calculator question. And you should get 1. So x equals 1. So the 0.11. And only 60% got it right. So it's likely that it might have been some sort of calculation error, or they might have complicated it by going by equating these two instead of just equating one of them to x. Okay, so we're almost at the end of the lecture. Let's see what the time is. Okay. Okay, so the graph of this function with the rule y equals g of x is shown below. It's a one-to-one function. Which of the following is most likely to be the graph of the inverse function? Okay, so this is a very, very common type of question. So what I like to do is I like to sort of outline y equals x. So it's a bit of a guide for me to figure out how the inverse function will look. Okay, and then it reflects. Okay, there's one. Reflects along the line, something like that. Okay, so let's see which one looks the most familiar. D, definitely out of the question, because this is reflected, so it's supposed to be here like that, and here, this is out of the question. This is definitely out of the question. Why is there a straight line on top? See, it's not going to work. So it's either A or B. So with A, it's looking really good. It's looking like what we want. With B, The only issue is this point here. It's supposed to be like this. So that's why A is the correct answer. So we've eliminated all of our options and we've narrowed it down to make A the correct answer. Okay, so that's literally it for methods. That's the end of the lecture. We've finished all the slides. Basically, we've covered quite a lot of key skills. So we've covered linear, we've covered set and function notation, we've covered functions, quadratics, inequalities, rational functions, square root functions, circles, domain range, and inverse functions. So it's a whole lot of content. I think a good way for you to try remembering it is, maybe take notes from the lecture, but then go away and a few days later, have a look at your notes. And that like repetitive exposure will actually help you remember it a bit better. Remember, you can ask your questions on the chat and they will be answered live. So I'll actually be live and I'll be like typing up all the responses to the questions. This is actually really good because I'll be able to answer more of your questions. So that's really great. So ask questions and all of that. A few tips before we finish off. So a few tips for methods. Firstly, bound reference is a really important resource. So make sure that you start preparing your bound reference early. So not like 2 days before an exam or 2 days before the SAC. You don't want to do that. You want to consistently prepare it over the year. In your bound reference, you should maybe add, obviously, the notes, the concepts that you're struggling with. CAS tips, because if you're allowed notes, you'll be allowed to use your CAS. So have your CAS tips on your bound reference. Have some tricky practice questions, so maybe any questions that were tricky. So have like the working out for it, any tips to solve different questions. And something that I found useful for myself personally is on the very front page, literally on the cover of the bound reference, writing a list of the mistakes that I commonly made was really helpful. So for example, when working with inequalities, swap the negative sign when dividing. So swap the inequality or swap the inequality sign when multiplying or dividing by a negative. So key mistakes. Some of the other mistakes that people make: draw both sides of a hyperbola, draw both sides of a trunc, so both parts, the up and the down part. So it's really good to write that. So after you do some practice, you'll start to notice that, you make some common errors. There's some errors that, you need to look out for. That's something good that you might want to write. Okay, so bound reference, I've talked about that. It can be as long or as short as you like. My bound reference was, I think, maybe like no more than 10 pages. So the aim of a good bound reference is you use it as little as possible. So that's your point. So you make an amazing bound reference, you use it throughout your preparation, but when the exam comes, you want to use it as little as possible. And that means that you have made a good bound reference. Okay, so that's about bound reference. Time management. So methods is a really content-heavy topic. There's a lot of content, a lot of things to remember and apply. So it's a good idea to pace yourself, do a little bit of methods every day, so that it doesn't get overwhelming. So make sure that you're up to date with class. Make sure you're doing your practice questions, staying up to date, doing the harder questions as well. So if you don't have a lot of time, don't spend all of your time just doing one type of question. So do a little bit of fluency questions. So fluency questions are questions that just test whether you understand it. Do some problem solving questions. So sort of like extended response, where you practice using your CAS as well. So make sure you do different types of questions and expose yourselves to different types of questions. Okay, so that's questions. Exam and SAC tips. So when you do an exam and SAC, obviously make sure you pace yourself through that SAC. So be aware of how much time you have and allocate specific time. And during reading time, read all the questions, and in your head, you can already see which questions that you're good at, which questions you might need to work on as well. So those are some tips that you can use. I think that's about it. If you have any specific questions, obviously you can ask them in the chat and I'll answer them like as soon as possible. But yeah, that's it for the lecture. So at the end, good luck for term 2. Good luck for the rest of this term. And I hope you have an amazing holiday.